Welcome to Calculus 1. In this lecture, we will be talking about continuity. Let's begin by considering three different functions: the function of f of x, g of x, and h of x. Note the value of each function at x is equal to 0, as well as the limit of the functions as x approaches 0. So the limit of each of the functions as x approaches 0 is equal to 10, but note the following: f at 0 does not exist, g of 0 is equal to 3, and h of 0 is equal to 10. Additionally, only h of x is continuous at x is equal to 0. So what does it mean exactly for a function to be continuous? So I'll now provide two definitions of continuous. Let c be a real number, and f be defined on an interval centered at c. We say that f is continuous at c if the limit of f of x as x approaches c is equal to f of c. So this is our first definition of continuous. And note that in this definition we use the limit notation. However, we can provide another definition of continuous that leverages the epsilon delta definition of the limit. So let c be a real number, and f be defined on an interval centered at c. We say that f is continuous at c if for all epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Now note the following. In our definition of a limit, we say that 0 is less than the absolute value of x minus c is less than delta. This means that x cannot equal c. However, in our definition of continuous, we say that the absolute value of x minus c is less than delta. So this means that x can equal c. And that is a very notable difference between the definition of a limit and the definition of continuous. Now let's talk about removable discontinuities. So an easy way to think about removable discontinuities is if there's a hole in the graph of the function, but the limit exists. And we've already seen this before. For example, consider f of x, where there's a hole in the function at x is equal to 0, but the limit exists. Additionally, consider the function g of x. There's also a hole in the function of g of x, but the limit exists. So this discontinuity is also removable. Now I'll provide somewhat of an unsatisfying definition of a non-removable discontinuity. So a discontinuity is non-removable if it's not removable. For example, if there's a jump discontinuity like this, where there is a hole in the function at x is equal to 0, but the limit does not exist, then we say that this discontinuity is non-removable. This is another example of a non-removable discontinuity. Here, as x approaches 0, the function tends towards positive infinity, so the limit does not exist. We also say that this discontinuity is non-removable. And finally, if the function oscillates infinitely between 2 points, then we also say that the function is discontinuous and has a non-removable discontinuity. Let's now define one-sided continuity. So let c be a real number, and f be a function defined on an interval centered at c. We say that the function f is continuous from the left at c if the limit of f of x as x approaches c from the left is equal to f of c. We can do the same thing for right-handed continuity. So we say that the function f is continuous from the right at c if the limit of f of x as x approaches c from the right is equal to f of c. Further, if f is continuous on the left, as well as the right, at the point c, we say that f is continuous at c. So let's go over an example of one-sided continuity. Consider the function f of x shown here. We can see that f of x is discontinuous at x is equal to 0 because there's a jump discontinuity, so the limit does not exist. Further, f of x is discontinuous from the left at x is equal to 0. This is because the limit of f of x as x approaches 0 from the left is not equal to f of 0. Finally, f of x is continuous from the right at x is equal to 0. This is because the limit of f of x as x approaches 0 from the right is equal to f of 0. Moving on, let's define continuity on an interval. There are two definitions that I'll provide here. The first definition is continuity on an open interval. So let f be defined on the open interval a to b. We say that f is continuous on the open interval a to b if for all c in the open interval a to b, the limit of f of x as x approaches c is equal to f of c. Things get a little bit trickier though when we try to define continuity on a closed interval. So let f be defined on the closed interval a to b. We say that f is continuous on the closed interval a to b if for all c in the open interval a to b, the limit of f of x as x approaches c is equal to f of c. Additionally, the limit of f of x as x approaches a from the right must be equal to f of a. and the limit of f of x as x approaches b from the left must be equal to f of b. If these conditions are met, then we say that f is defined on the closed interval a to b. Let's now talk about the continuity theorems. This will be pretty easy because the continuity theorems are parallel to the limit theorems. So let f and g be functions defined on an interval centered at c. First, we have the constant multiple continuity theorem. This states if n is in the real numbers and f is continuous at c, then n times f is continuous at c. We also have the additivity continuity theorem, which states that if f and g are continuous at c, then f plus g is continuous at c. The product continuity theorem states that if f and g are continuous at c, then f times g is continuous at c. And the rational function continuity theorem states that if f and g are continuous at c, and g of c is not equal to 0, then f divided by g is also continuous at c. I won't prove these theorems, but you can prove them quite easily using their corresponding limit theorems. Finally, let's move on to the composite function continuity theorem. First, recall that there's no composite function limit theorem. That is, if the limit of f of x as g approaches c is equal to L, and the limit of g of y as y approaches L is equal to m, we cannot conclude that the limit of g of f of x as x approaches c is equal to m. However, there does exist a composite function continuity theorem, and this theorem states the following. If f is continuous at a, and g is continuous at f of a, then g of f of x is continuous at a. To solidify this, let me go over an example. Let f of x be equal to tan of pi x squared divided by 4, which is equal to f of g of x. Here, g of x is equal to pi x squared divided by 4, and f of q is equal to tan of q. We want to determine whether or not f of x is continuous at x is equal to 1. First, notice that g of x is a polynomial, so it's continuous everywhere, and g of 1 is equal to pi over 4. Further, f of q, which is equal to tan of q, is continuous at q is equal to pi over 4. So if q is equal to g of 1, then f of q is equal to f of g of 1. So by the composite function continuity theorem, f of x is continuous at x is equal to 1.